But in general, where does fatty acid catabolism occur? Mitochondrial matrix, because the anabolism is occurring in the cytosol. Okay, up to what point? Palmitate, which has how many carbons? 16. Okay, and it's always saturated fat for that part, because we're going to find out what happens whenever we need to get more complicated, either desaturation in particular. All right, so to make the long-chain fatty acids, palmitate is the building block. So you use fatty acid synthase in the cytosol to get it up to 16. Then thioesterase is the one that is the enzyme portion that will cleave off the palmitate, okay? And then the palmitate is shuttled into the ER. And in particular, it's going to be the smooth endoplasmic reticulum and to an extent in mitochondria as well. But primarily the smooth ER. And so then then you can desaturate it. And what does that mean when we say desaturate? You're going to make double bonds. What kind of double bonds are you going to be making? Cis. They are only cis double bonds. Okay, and we'll talk a little bit about that and the enzyme that's involved with making the double bonds. Now, the hepatocytes can easily go all the way up to carbons 9 and 10. So just like, for whatever reason, the fatty acid synthase can only make up to 16 and it has to stop, the hepatocytes the ER can only add in the double bond as far as between carbons 9 and 10. However, for a lot of the PUFAs, where are those double bonds located at? Much closer to the end, like the omega-3s, omega-3, 6, omega-6. So we're talking about 9, 12, 15, and 18 carbons down. And so it can do the first one at 9, but it couldn't do the ones beyond that. Right? So, therefore, mammals are going to require fatty acids from dietary plant material, because plants are the organisms that can desaturate the long-chain fatty acids.
So then, how do you get the amino acids from fish?
So, I mean, fish do have some of the omega-3s as well, but yeah, primarily we're getting them from plant materials. Well, fish aren't mammals.
Oh, I thought you said ants.
No, sorry, mammalian. Not animalian. I don't know. All right. So this is done by the complex called fatty acyl-CoA desaturase. I didn't ask you to name that. I mean, that's pretty simple. I mean, it tells you exactly what it does. And it's fatty acyl, not acetyl, because it can take, it can take things that have more than 2 carbons. But it's very complicated. It's called a mixed function oxidase. Is a class of enzymes. And that's because there are 2 different substrates that get oxidized simultaneously. And so in this example here, not only are you oxidizing the fatty acyl chain, but you're also oxidizing ultimately NADPH. Because what happens is, in order for the fatty acid, the saturated fat, to become an unsaturated fat, it utilizes the cytochrome B, which has iron. So iron has to give up the electron. Okay, so that way it becomes iron 3+, and you regenerate that at the expense of an FADH2 becoming an FAD, and then you regenerate the FAD by using up an NADPH. So that's why at any one time here we're oxidizing the saturated fat as well as the NADPH. And I'm going to talk a little bit about this. It's called an oxidase, but, we'll just talk about that in just a moment. Because you don't want to get confused between oxidase and oxygenase. There are a handful of exceptions, though, but for the most part, they're pretty cut and dried, like what makes an oxidase, and what makes it an oxygenase. All right. So we can make all the way up to palmitate. Oops. There, we can make all the way up to palmitate. And we can make palmitoleic, which is a 16:1 delta 9, which, once again, I don't expect you to memorize the names of, oleic, palmitoleic, linoleic, all that kind of stuff. I just want you to be able to draw it if I gave you the 16:1 delta 9. You should be able to draw that, because that tells you 16 carbons, there's one double bond, and it starts between carbons 9 and 10. All right, so in the ER, we can also go and make stearate and oleate. Okay. However, we can't go beyond that. So the next one would be linoleate, or linolenic acid. If you're going to talk about it being a carboxylic acid. And that's going to be happening in our plant diet. And so if you notice, the linoleate and alpha-linolenate are highlighted. Okay, and so why are they shaded? Those two in particular, unlike arachidonic, which is the arachidonate down here, which has 4 of them. Why is the linoleate and alpha-linolenate shaded? They're omega-3s. Maybe. What else? I mean, are they really omega-3s? Is linoleate an omega-3? If it has 18... No. Right, it's not. So why are they shaded?
They're important for something.
They are. They've got a special name that's very hippie-ish. I don't know. You hear... It's a good buzzword. What kind of fatty acids are they? They are the essential fatty acids. Those are the 2 that you've got to get from your diet.
They are important for something.
They are. They are essential. It's like the old Jeopardy joke, that was on Cheers many years ago when Cliff Clavin got on Cheers. And I forgot what the question was, but it's like, what do these 3 people have in common? And Final Jeopardy question, he put they were 3 people who had never been in his kitchen. He's like, that's true, they've never been in my kitchen. Okay. All right, now once you have linoleate, then we can go ahead and desaturate, because the arachidonic acid, if you notice, they are at closer carbons to the alpha end of the compound, and so that's why we can go ahead and desaturate it and elongate it and so on and so forth. But you have to get the linoleate first. Okay. So those 2, linoleate and linolenic, are the 2 that you have to get from your diet. And so if you just ate no fish, no nuts, solid red meat, that's not good. So unless you take some type of supplement.
So we can only go up to oleate, and then...
Right, for anything that's going to be desaturated.
And then we have to have...
Then you have to get the next building blocks from... We would have to get it from our diet. Plants can go ahead and keep on going.
To make linoleate.
To make anything beyond...
Oleate.
Yes, from linoleate.
We're not getting linoleate from our diet. We're getting the things that make up.
No, you get the linoleate from your diet. Because it's a polyunsaturated fat. It's one of the good fats. That's an omega-6 fat. Okay, and then omega-3/6 would be the alpha-linolenate that you get. So the 2, was that pink or orange? Pink? Pink ones are the ones that you want to make sure you get from your diet. You get other ones from your diet as well, but it's like, if push comes to shove, those are the essential ones for life.
I guess I was just wondering, because I was wondering why it was like a full chain instead of like separate.
Oh, so you mean between the 18.1 and 18.2? Well, we don't study plants. I'm assuming that it's probably a multi-step process. Because the only difference is there's a double bond difference between oleate and linoleate. There's only one double bond that's different between those 2. See, one's 18.1, one's 18.2. They don't add any more carbons.
Because if we have oleate, then why?
Because we can't put the double bond at position 12. We can only go to position 9.
But then it says it leads to linoleate. Is that just saying?
It leads to linoleate in plants only.
Okay. Oh, I see. Okay.
So plants can keep on going.
Not at my Garcia.
Plants can keep on chugging along. You can't. You're stuck at oleate.
Do not pass go. Do not
Yes.
linoleate.
Do plants just mainly use like fatty acids for membranes, or
Well, they can also use them for energy, I do believe. I mean, I'm not a botanist, but they can utilize it for energy.
be interesting to see like a fatty,
To see a what?
like a fatty plant, like a Dr. Straw plant?
Yeah.
Did you just put up some back?
I think that he did.
Like his mouse, like his mouse.
Well, I mean, it's a different lipid profile.
Yeah, I don't know. I did.
I mean, that's why seeds have all those lipids in them, because, they use the glyoxylate shunt and everything.
Oh, I couldn't.
But,
Dr. Straw, his mouse.
so, the one thing I suggest, and hopefully you did this for your interview, have the words roll around in your head before they come out your mouth.
I don't think Dr. Straw's that sensitive about his figure.
Yes, story.
So, projects that are not in the pink box after linoleate, can we synthesize those in our bodies?
Once we have the linoleate.
Okay.
Because if you notice, the double bond in the linolenate, the gamma linolenate, is at position 6.
But what about the one that's at 14 and then it goes?
That's because it gets elongated, so it was already at 12, and then we added 2 more carbons on. So now it went from 12 to 14. It's like a little assembly line, yeah, in the ER. Okay. I've already mentioned the reason why it was important. Okay. In the event that, ultimately we're making like a arachidonic acid, which we're going to find out is a precursor, biological precursor for a lot of other molecules as well. So that's why you have to make sure that we get to the arachidonic acid. And it has I don't remember it right now off the top of my head, but it's the one that's really kinky, and so it has the very disturbed melting point, to where you don't have to worry about it clogging your arteries per se. All right, so the arachidonic acids, or acid, I should say, goes on to make eicosanoids, and 2 examples of broad classes of compounds that are eicosanoids are the prostaglandins and thromboxanes. Prostaglandins, does anyone know why they're called prostaglandins? First of all, do women have prostaglandins? Yes. So why are they called prostaglandins? What are they named after? The prostate of sheep, I do believe. I think it was that because that was the first tissue, and they just thought it was a male hormone or whatever. But it's not. Women will also have prostaglandins, so it's kind of a misnomer. And then thromboxanes. All right. So now I just wanted to talk a little bit about the enzyme names. So we've used the term oxidase. And then now we're starting to hear oxygenase in the way that they're different. Technically, both of them are in the overall big family of oxidoreductases. There's only the 6 or 7 enzyme classification families that get further subdivided. Oxidases, in general, are enzymes that catalyze oxidation reactions, and they utilize molecular oxygen, O2. But the oxygen is not in the final product. Okay, so you are not making what kind of functional groups here? Like hydroxyls, they will not be used to make an alcohol, a ketone, ester, any type of acyl group. It's just that the oxygen is what's, using the electron acceptor. So we've seen an instance of this already. Like you could imagine one way that with ATP synthase, the fact that, all right, cytochrome C oxidase, the cytochrome is oxidized, but there's no oxygen atoms that's actually added to it. Because actually, technically, if you look at it from the point of the water, I guess ATP synthase would be an oxygenase. Okay. There are some exceptions historically where they still just call it an oxidase, even though it's really an oxygenase, so it's not a cut and dried rule. But people usually will understand what you're talking about. Oxidases, you have oxygen, but the oxygen is not incorporated in. Whereas an oxygenase is an enzyme that uses the oxygen, but the oxygen is directly added to the product, or at least one of the products. So this is where you can make some type of ketone, a carboxyl acyl group, an alcohol.
And this uses O2.
Right.
Uses milk.
Mm-hmm. Yeah, typically it was O2.
They both are always involved in redox.
Pardon?
Are they both always involved in redox? Right?
Well, by definition, if you're oxidizing something, it's going to be in a redox reaction. It's just like what is doing the oxidizing and where does the oxygen ultimately end up. So, an example is cytochrome P450, which we'll talk a little bit more about that. And it's actually, there are families of these cytochrome P450s, but it takes an alkyl group or an alkane and turns it into an alcohol, which is really nice for us. Okay. And so since the oxygen got incorporated directly into what had been the alkane, then it would be an oxygenase. Then the oxygenases are further subdivided to monooxygenases and dioxygenases. Mono means only one oxygen gets added into the product. Dioxygenases means both do. So maybe it's a diol, maybe it's a ketone and an alcohol, or carboxylic acids being made. You're getting both of the atmospheric oxygens added into the product. So that's why it's a dioxygenase.
So wouldn't that make it radical?
Pardon?
Oh, never mind.
I'm so glad you can talk yourself out of it. Okay, so there's monooxygenases, dioxygenases. So this is an example. I mean, it's tryptophan 2,3-dioxygenase, and so if you notice here, it adds in an acyl group as well as what will become an amide. Technically, it's a 4-mel group because it's only got one carbon.
Do you want us to memorize that enzyme?
No, I mean, if I hid that name, you should be able to say, hey, that's a dioxygenase. And we're going to see other oxygenases later on, because sometimes with the neurotransmitters and things like that. Or, does anyone know what's an example? Unfortunately, I can't see what the next slide is in a few minutes. What's an example of, like, have you heard of any famous, important medical oxygenases that get, there are a lot of medicines that target anyone in particular? They're usually abbreviated because you don't want to say a really big name for it.
Cyclooxygenases?
Right. Yep. Those are more commonly called COX, the COX enzymes. COX-1, COX-2. So that's a cyclooxygenase. So it's going to add in the oxygens. It's just a cyclic at the end. All right, so the P450s actually is a huge family. I mean, they all have hemes. There's at least several hundred of them, and so that's why they do different types of specificities. But this one in particular that we're showing here is going from an alkane to an alcohol. And if you notice here, it would be just a monooxygenase because the alkyl group only receives one. Water is then given off.
So if not, nothing would be given off.
Pardon?
Like water wouldn't be given off if both were.
Right, right. And that tryptophan 2,3-dioxygenase, both of the oxygens that were colored, and both of them were included into the final product, final organic product. And you could say, see, this one's also a mixed oxidase because two things are being oxidized at the same time, but it's technically a dioxygenase because one of those products is receiving, it's technically a monooxidase because one of those products is receiving the oxygen from the O2. So, eicosanoids, we talked a little bit about them, I do believe, last semester, towards the end when we did some of the signaling stuff. They're biological signaling molecules, but they're only short-range messengers. Right? So, what kind of the CRIN system, CRINE, is that? It's a paracrine. Okay, I didn't want to give it away. Versus, something like a hormone that travels long distances. This one is only short-range messenger, so it only affects the local environment. Which should make sense once you see them, because, they're made from arachidonic acid, and so you don't want all these big fatty molecules floating around all over the place. All right. So we have the COX enzymes. Those are cyclooxygenase enzymes. It's called prostaglandin H2 synthase as an example. And in mammals, mammalian, not animal, but mammals, we have two isoforms. We have COX-1 and COX-2. COX-1 is what helps with your digestion because it helps produce acid in your stomach. And COX-2 is the one that you commonly think of with respect to, like, if you have a headache, for fever, pain, things like that, inflammation.
So, our body uses hormones to signal for pain.
Well, yeah, otherwise you wouldn't have pain.
Seems,
Like, what is the purpose of pain? You can either get really theological here, or you can become biological.
Tell your body that something's wrong.
Right, it tells you something's wrong. Take the hand off the stove, like Hershey.
Well, I would think a hormone would be like too long acting.
But that's why this one's this one's a. Unfortunately, some of that got cut off because a little alarm went off over here. So phospholipases free up the arachidonic acid, or arachidonate in this instance, and then we have the COX enzyme that will turn it ultimately into the thromboxane or the prostaglandin that you need. And this is where aspirin, ibuprofen, the NSAIDs, which stands for non-steroidal anti-inflammatory drugs, that's where they interact. And so what some of the issue is that you have to be concerned if it's not specific. If it affects just cyclooxygenases in particular, what is one of the side effects? What's the side effect of having too much aspirin? Stomach issues. Yeah, death as well, eventually. But yes, stomach issues because it's inactivating. By the way, aspirin is irreversible. It's a covalent attachment where the important serine got, acetylated. Whereas the naproxen and things, that's not. Okay, so that one is not... it's a substrate mimic. It's not being a covalent intermediate here. Okay? So that's why those are the non-steroidal anti-inflammatory drugs. Aspirin is acetylsalicylic acid. Okay. So these resulted in a lot of unwanted side effects. They showed that they were able to make, and for those who had medicinal chemistry before, they used it as a lead to try to make an analog that would only be specific for COX-2. And in the 1990s in particular, especially the late 90s to early 2000s, this really blew up because they figured out how to knock out COX-2 only. So therefore you wouldn't have the stomach problems and things like that. They thought these were miracle drugs. This is your Vioxx, your Bextra, and Celebrex. However, Vioxx and Bextra both now have been taken off the market from the early to mid-2000s because they were potentially fatal side effects. In fact, there have been huge lawsuits. Celebrex you can still get, even though there's still lawsuits out there. Because what were some of the side effects from, like, Vioxx?
Yeah.
Right, death. That is the ultimate side effect. Unwanted, usually. And so, but no, there's due to fatal strokes and cardiac issues. So yeah, they could die, where people had an increase in heart attacks. Okay. All right, so that was it for this section. Are there any questions? Yes?
I've heard that, so there's, some people who don't, feel pain, right?
Right.
So, what about people who don't feel, brain freezes? What is the function of a brain freeze?
That I don't know. We may have to look into that one.
There you go, Corey.
So,
Yeah.